Steinhauer here, welcome back. We are discussing Einstein's theory of general relativity and how it explains gravity based on the curvature of space-time. And we've got a diagram here that shows how that curved space-time works, let's say in the solar system, right? You've got the planets who are trying to move in the straightest line they can, but straight lines in curved space look curved to outside observers, right? And so the only reason that the Earth is moving in the ellipsoid circle that it is because the space-time, the sun is warping the space-time in our environment, and the Earth, the straightest line that it can make is that curved path. If objects are moving too fast, like this comet, they will move in and then exit out on the other side. Mars, on a larger orbit, experiences less curvature out there, and so feels less gravity, and so is moving on a larger and slower orbit than the Earth is. If you've ever played with those toys in science museums, which look like this, where you drop a quarter in and you watch it orbit around and it slowly moves down and eventually moves really fast and then drops into the bottom, this is pretty good analogy for how gravity actually works. The only reason why that quarter will spiral inward is because it's feeling some frictional forces. If there were no frictional forces acting on that quarter, it would continue in a circular or elliptical orbit, in perpetuity, forever, just like the Earth orbiting the sun. The next time you do go to one of those science museums and see one of those things, grab yourself a roll of quarters and do some experiments, because it's really cool. You can see pretty much all of Kepler's laws in action. So start off with the quarter at the top of the ramp, and it will enter a fairly circular orbit. And again, that orbit will decay because of friction, but it's going to be a pretty circular orbit. But you'll see that the orbital period, how long it takes to go around once, changes and gets smaller as it moves closer and closer to the center. It will get fast. The velocity will go faster, the quarter will be moving faster, and certainly the time that it takes to make one complete orbit will go way down as it moves towards the center. There's two of Kepler's laws right there. You can see Kepler's area law by, instead of starting the quarter at the top, start it like halfway down. Starting it halfway down will give it a little bit less velocity. And so instead of doing a circular orbit near the top of this object, you'll see it dip down into the shape and then come back up, and then dip down and then come back up, and then dip down. It will enter an elliptical orbit. And guess what? That object that is the focus of that curvature at the center will be at one of the two focal points of the ellipse. And guess what? The quarter will be moving faster when it gets towards the bottom, near the object at the center, and it will be moving slower when it's up at the top near the starting point. And so you can see Kepler's laws in action in a very real way if the shape of this thing is right and you start your quarter with the right velocity. So check that out the next time you're at one of those museums. Okay. Another interesting difference between Einstein's theory and Newton's theory is that Einstein predicts that time will also be affected by gravitational forces. In other words, it's a curvature not just of space, but of space-time. And the stronger the curvature where you are, the slower time seems to move for you. So in other words, the closer you are to a very massive object, the slower time will move for you. And this has been actually tested. If we have two clocks that are very precise and we calibrate them on the Earth and we leave them on the Earth, they seem to run at the same rate. If we put one of them even in orbit around the Earth, move it a little bit further away from the Earth's gravitational field, meaning that the curvature is a little bit smaller out there, then that one shows moving faster than the one that we leave on the Earth. But that is a measurable effect that we've been able to see. In fact, if you don't correct for this time behavior, the global positioning satellites, our GPS satellites, don't work. You have to take this correction of the time difference between being on the Earth and being in orbit into account, or you'll get your positions wrong. And so all of these equations have to be built into the correction factors that the GPS satellites use so that you can navigate, to the grocery store and back. Okay, there's one more concept that we need to understand before we can really get to black holes, and that's the concept of escape velocity. We've talked about this at some level before in this class, but let me remind you. So we know that if we throw an object up in the air, the gravitational force will slow it down, and eventually it will reach zero velocity, and then it will fall back down to Earth. If we throw it faster and faster, straight up, away from the object that we're feeling the gravitational force from, it will get higher and higher and higher before it stops and turns around and comes back. It turns out that there's a specific velocity at which that object will no longer return to the Earth. It's not that an object ever escapes the Earth's gravitational field, although we sometimes use that terminology. The 1/d² law of light still works. And even though d gets really, really big, the force of gravity never goes to zero. But if you're moving fast enough, that force of gravity becomes small so fast that the acceleration that object feels is never enough to turn it back around. And in fact, there's a specific velocity at which the object will achieve velocity zero, meaning it will turn around, but only at distance equals infinity. Right? If an object has a little bit less velocity than that, it will achieve that velocity zero at not infinity, and then will come back and eventually fall back down to the Earth. If an object has more velocity than that, a greater velocity than that, then it will have some non-zero velocity. It will still be moving away at some non-zero velocity, even at distance of infinity. But that the escape velocity defines the hairline between an object that will eventually fall back to the Earth and an object that will never fall back to the Earth. It will continue moving far away for all time. And this is the equation that gives us that velocity. The escape velocity, let me write it over here because it might be a little bit hard to understand. The escape velocity, that's what I'm calling VE here. The escape velocity squared is equal to 2 times g, our normal gravitational constant, times m divided by r. So VE, again, is the escape velocity. It's going to have units of velocity, so kilometers per second or meters per second or whatever you want to use for your distance and time unit. G, of course, is the gravitational constant. (6.67 times 10 to the negative 11 meters cubed per kilogram times second squared. M is the mass. Now, we've got two objects here. Which mass is it? It is the mass of the object whose gravitational field you are trying to escape, right? If I'm throwing a baseball up into the air from the Earth, it is not the mass of the baseball. It's the mass of the object you are escaping from. So in this case, it would be the Earth, but you could be any other real object that you wanted to escape the gravitational force from, and that would be in kilograms. R is the distance to the center of that mass. And again, this can be a unit of meters or kilometers, or you're going to probably need something, if you're doing this, meters. If you're going to use this G thing, you better be meters here because you're going to need to cancel those out. Okay, so what is the escape velocity? Let's try this equation out, see how it works. What is the escape velocity from the surface of the Earth? The mass of the Earth is 6 times 10 to the 24 kilograms. The radius of the Earth is 6.4 times 10 to the 6 meters. And that is important because if I am standing on the Earth and throwing a baseball up, that is the distance, the radius of the Earth is the distance between that ball and the center of the Earth when I let it go. Let's just draw a quick picture here. Here's the Earth. Here is me standing on top of it, not to scale, and throwing a ball. The distance between myself and the center of that Earth is the radius of the Earth. And so the radius of the Earth is if I'm standing on the surface, the distance of interest. If I'm in orbit, or if I'm standing on the moon, or if I'm further away, that number will increase because I'm further away from the center of mass of the Earth, and the radius and the escape velocity should go down. Okay, let's think about doing this calculation. We know that the escape velocity squared is 2 times g times m divided by r. We've got all these numbers. We can just plug them in. That's 2 times 6.67 times 10 to the negative 11 meters cubed per kilogram times second squared. We know that the mass is 6 times 10 to the 24 kilograms. We divide all that by the radius, 6.4 times 10 to the 6 meters. This, of course, is the velocity squared. If we want to take the square root now of both sides to get the velocity, we should do that. So the velocity will be the square root of all of this. Plug that into your calculator, you get 11,000. Now, what are the units on this number? Well, let's work on it. We've got a kilograms canceling a kilograms here. We've got a 1 meter down here canceling one of these 2 meters up here. So inside the square root, we've got a meter squared on top and a second squared on the bottom, which is good. That's going to give us meters squared per second squared. When we take the square root of that, we get meters per second. Sometimes we like to write this as kilometers per second. There are 1,000 meters in a kilometer. We can divide this by 1,000 and we get 11 kilometers per second. That's pretty darn fast. 11 kilometers per second, right? Nobody can throw a baseball that fast. And in fact, it's difficult to get anything moving that fast that has any sort of substance to it. And so this is, the implications though are, if you want to send somebody to the moon or send an object to Mars, you have to get, and not provide fuel the whole way, you have to get them moving at least 11 kilometers per second, because that is how fast you need to be moving in order to leave the Earth's gravitational field and not be pulled back eventually. You might remember this is similar to the orbital speed. At low Earth orbit, the orbital speed of objects orbiting the sun and orbiting the Earth in perfectly circular orbits is about 8 kilometers per second. So again, in order to get an object in orbit and staying there, you need to get it to 8 kilometers per second. You need to get all the way up to 11 kilometers per second if you want to go somewhere else in the solar system. Okay, here's a thought question for you. What happens to the escape velocity from the surface of an object if you shrink that object? Let's think about the formula. Escape velocity squared is 2 times g times m divided by r. If you make an object smaller, what are you doing? You are only changing this radius variable, right? From the surface of that object, if you make it smaller, r gets smaller because you get closer and closer to the center of that object. And so if r gets really large, the smaller r gets, the larger this escape velocity has to be. And so the escape velocity, as you make an object smaller, has to go up. And so if you go from something the size of the sun and the mass of the sun and shrink it down to, say, a white dwarf, the escape velocity from the surface of a white dwarf is much larger. And if you shrink it down even more into a neutron star, it gets really, really large. That escape velocity goes up and up and up as you make this thing smaller and smaller. Okay, we'll come back in the next video and talk about the implications of that and how we can make a black hole and what it means to be a black hole. See you then.